guys, welcome back to the Physics channel. In this video we are going to continue with our derivations in electromagnetism. So in this video particularly we are going to be dealing with derivation 2, and this is the divergence theorem. It's a very fundamental theorem of physics which literally describes how a thing or a field spreads in space. So divergence talks about the spread from a unit volume through some closed surface. Okay, in that case, to begin, we have to state a few things that are important. Obviously, we're working again in rectangular coordinates, but consider the following diagram. So we're going to draw this diagram in three-dimensional space. It could have been any shape that we would like to draw, but let's start by drawing the Cartesian plane. So we start by drawing the z-axis, and then the x-axis, then the y-axis. Then we draw some shape. Let me make it a cube for the purpose of this derivation. Could have been any particular surface, but I prefer to work with a cube. So let's draw a cube. Let's draw all the particular sides of this particular cube. It's going to be a volume tau, right? So this is the z-axis, that is the y-axis, all right, y-hat direction. Z direction, and of course the x hat direction as well. So this particular surface will be a surface S, but let us do something. Let's say this is not a huge volume, but it's an element of volume. So initially we called it tau. So let's say this is an element of volume in space, right? An arbitrary element of volume in space. Let's call this volume d tau. So we said it is how a field spreads from a unit volume d tau through space. So once we have done this, let us define a flux. Assume there are field lines that are penetrating this particular surface at different directions. So let's say there's a field, and let's say this field is given by some vector, which we call the vector A. All right. So this vector A, to define the flux, is the A vector dot producted by an area in which this vector penetrates. So this is what flux is by definition. Or in our situation, since we have an element of volume, we deal with an element of flux. So we define phi to define the flux in this situation. Okay, therefore we have that the A vector, which is the field, dot producted by an element of area dA gives us an element of flux. That's the definition we're going to use. What we are really saying is that A is a vector which penetrates that surface from different directions, right, from different parts of this particular surface or different areas on this particular volume. Okay, so now that we have defined that, we also want to say something about this particular vector. So it won't be just any random vector. Since we're in rectangular coordinates, we are going to consider a field which is given by the following equation. A vector which is going to be the x component in the x-hat direction, right? The y component of A in the y-hat direction, and of course the AZ component in the z-hat direction. So we'll calculate the flux from some vector field A, and we want to talk about how does this vector spread through space on some particular surface. So A is this particular vector which is going to penetrate this particular surface. And we are going to mention that this particular vector interacts, right? It interacts with that particular surface or that volume tau, right? So in this case, let's just say it interacts with this particular volume d tau. Okay, let's proceed to the next phase of this derivation. Okay, so A has a flux of field lines. So it's not just a single line, it's a flux of them. So it could be billions and millions of field lines that penetrate this particular surface. So these enter this particular surface tau, and they exit the same surface on the other side. Okay, so I think the best way to visualize what we are talking about, this particular vector entering and exiting, the best way to visualize this would be to have some particular diagram or diagrams which describe the scenarios as we have them. All right, so in that situation, we could begin by describing the x-axis and see what happens. We'll let these field lines interact with this particular surface in the x direction. So we can go ahead and draw the z-axis, the x-axis, and then we can also draw again the y-axis. Then draw again the same particular surface tau or d tau, right, in this particular space, right? So we draw this nice cube that we have with all the sides defined perfectly. Okay, this is our nice cube. Then we proceed from this particular point and say, of course, we need to put the direction. There will be zx, z hat, y hat, and x hat. But let's consider this particular surface, since we're talking about what's happening in the x direction. So the surface at the front and the surface at the back, these are the surfaces which are exposed to this flux of field lines. Okay, so we can have a field vector A which comes in from the back. Then this same field is going to exit from the front of this particular surface. Okay, so I think this might be a good point for me to also maybe start by indicating my directions. But let's first say this is AX. So it's the X component of this vector field which penetrates this particular surface, and it comes from the negative side of this surface and penetrates it, and then exits on the positive side of this particular surface. Okay, so we have it like this. Then we're going to proceed again and label all the parts that we need and say, okay, the direction in which this particular vector is traveling, the x component, is in the nx hat direction. So it comes in from the back, then goes to the front, and that direction is the nx hat direction. Then we see that as this particular vector is traveling, it has an effect on the dy component and the dx component. So the area in which it affects is the dy and the dz. So let's mention the z hat and the x hat and the y hat direction on this particular surface. But we see that A interacts with dy and dz, both from the back and from the front as well. Okay, so let's just highlight to see that that particular red line would be showing this vector nx that we are mentioning. Okay. Of course, if you were to go the other way, which is back, you would then have negative nx hat, right? Which is not necessarily important, but yeah, just to indicate that the opposite direction would be negative of the same nx direction. Okay, now that we've mentioned this, it is then incumbent on us to then describe how does this particular vector interact. Okay, but before we do that, let's maybe consider the y-axis and see what's happening on the y-axis as we see the effect of this particular vector. So on the y-axis, we again do the same thing by drawing this x, y, and z axis that we have on this particular surface. All right, then maybe we label the z hat. We do the same thing with the y hat, and then we do the same thing with the x hat directions. Okay, now that we have done that, we may also then draw the same surface that we had before. So we draw again the same cube or the same d tau that we have, an element of volume tau. And we have this particular nice square or cube or rectangular prism, some particular surface which you can deal with the areas quite easily. We saw that the vector A was happening parallel or affecting the two sides that are on the y-axis, right? Or that change in distance depending on the y-axis. So we consider that back surface and the front surface. So the vector A penetrates from the negative AY side or NY a negative A direction and then exits on the positive AY direction. So we've got that positive one, and then we might also want to indicate that we've got negative and positive, and also we then notice that the area in which this particular vector or this flux of field lines affect is the dx and the dz components of this particular area. Okay, so that's good. We note that down. Then, of course, we proceed from this particular point as well and say, okay, let us now consider the z-axis to see what happens on the z-axis. So it's going to be the same procedure, just looking at the particular surfaces which are actually being affected in a particular direction, right, depending on the z, x, y, right, and then see what's happening. So we draw first at the z-axis, and then let's draw again the same surface or the same volume that we had before, that d tau. We draw a nice prism or cube that we have over there. Then once we label that, we then have to go on and proceed by describing again which surfaces are being affected. It's the bottom surface and the top surface. These are the two surfaces that are being affected by this particular vector or vector field A. So it goes up and exits in the positive side of AZ, but of course it comes down from the negative side, so that'll be a negative AZ direction. Okay. Then we would like to label all the directions because I labeled only for the X. So, I mean, before we do that, let's say here the dy is being affected, and of course the dx are the parts of the area that are being affected by this particular vector AZ. Okay, we note that down. Then we proceed on to labeling all the directions that we have in this particular, in these different scenarios that we have. So, we look maybe first beginning with this z and say that direction up, we're going to call it NZ. So that's the N hat in the Z direction. Then you label again the Y as well and say that direction in which the vector A goes, we're going to call it NY hat. Okay? I mean, those are the important directions. So we just circle them. So on the X, we are dealing with that NX hat direction. And of course, on the NY, we're dealing with the same thing. And on the NZ, we're dealing with the same direction that we have now labeled. So these are the things that we need to know. So the flux of these particular field lines affects these surfaces differently. So once of these particular diagrams, we now consider how to calculate the fluxes. So using the diagrams on the previous page, we are now going to proceed and actually calculate, right, the fluxes that we have in different scenarios, so the X, Y, and Z. So we shall start first of all by looking at the X, right? So if we're going to, the fluxes are going to be given by the following. So let me find a nice color. We're going to say for the X one, that will be the first one. So flux in the X direction, right? So that's phi X is going to be given by, remember it is the particular field multiplied by the area. So we see that it is AX, that's the field. And what does it affect? It affects the back part of the area, DZ and DY. So we have that. Then we also have the front part of this particular field line. It's going to be AX interacting with plus DZ, DY. But then the field AX also, we can calculate its partial derivative in the other different directions. So the partial derivative of AX with respect to the X direction, then multiply this by the full derivatives of dx, dy, and dz, since it also affects all those other directions as well. So this will be the first flux in the X direction. Then we do the same thing and consider then the Y flux, right? So phi of Y would be then given by AY is the field, and from the back side we have got negative dz multiplied by dx, so that's a small area. Then we say we add to this AY, which is the front part, dz multiplied by dx, so that's the front area. Then we say we also have the partial derivative of this particular AX with respect to Y, so it's affecting different parts of this particular surface, so we multiply this by the full derivative, dy, dz, and of course dx. Okay, having labeled this, we also can proceed with the same notion of thought and think about the z direction. So phi in the z direction, the flux in the z direction would then be AZ, which is the component of the field in the z direction, multiplied by the back or the bottom part of the particular area, which is dx multiplied by dy, negative of course. Then we add to that the top part of the surface, which is AZ multiplied by dx times dy. Then of course the partial derivative of AZ with respect to z, right, to z. Then we have got that multiplied by dx, dy, and of course dz. But we should notice something of interest here, that we have in all situations dx, dy, dz at the end. So why not give this particular thing a name, right? So let us say that we are going to consider that particular last term, dy, dz, dx, right? So we're going to call it just the tau or d tau, because that's a small volume and it's commutative. I could have said dx multiplied by dy multiplied by dz. It's the same thing as saying dz multiplied by dx multiplied by dy. So we just call it d tau. So that simplifies things so that we don't have to rewrite a long part of this particular expression. Then we consider that what would then be the derivative, the total flux, right? So what would be the incremental flux that we have? So the derivative of all these particular fluxes that we have, what would the value be? We have to add all of them together for us to get the incremental flux. But because we are doing that, we notice we will have certain things cancelling out. So d phi will lead to the following result, that az dx cancels with the top part, and the dz dy ax cancels out with the other part that we have on the other side. So all these other terms are going to cancel out, leaving us with the last term. So we will actually have the partial derivative of ax with respect to x. So that will be the first term, the first part, plus the partial derivative of ay with respect to y. So that we'll write that down there. Then we'll also have the partial derivative of az with respect to z. So that'll be the other expression. And all of these expressions that we have inside are all going to be multiplied by that particular volume element, d tau. Okay, so this is quite interesting. We notice something interesting here, that of course the reason why all these other terms were removed was because we added all these three equations, and that's why we see these terms all cancelling out, leaving us with the last expression, giving us the incremental flux. Okay, so that is fine and well. So we can still proceed with our derivation. Now, we have to note something that is important. What we have in that particular expression, perhaps I should rewrite it and say d phi that we had and we were given there. We said this was equal to the partial derivative of ax with respect to x. We also say this is plus the partial derivative of ay with respect to y. And this is also plus the partial derivative of az with respect to z. And of course, we said all this was then multiplied by that element of volume d tau. But we notice something, that what we have in this bracket is actually the gradient of the scalar field acting on the area. So nabla dot a also acting on the vector field, because the direction has been removed. So we assume ax and ax, ay, az, and of course on the nabla term we have got an x component, a y component, and a z component. So those removed to give us that expression. So we actually can simplify this whole above equation to simply be the following: nabla of, so the gradient of the scalar field. In fact, we are now going back to the notion of the spread of the scalar field. So nabla dot a, which is the vector, all that multiplied by some particular volume d tau. But as we have now come to this particular point, we realize at the beginning of our derivation, we had stated something that is important. We said that the element of the flux, or this particular d flux that we have, right, is given by the area vector dot producted by the area. So I mean the field vector dot producted by the area. And we said this was the flux. Okay, but then now we see that these two equations are actually equivalent, because we can just equate the left-hand side and the right-hand side. And so because of that, we end up with a simplified equation which combines these two notions. And this is this vector field A dot producted by the element of area is actually equal to nabla dot producted by the field vector, and all that multiplied, of course, by the element of volume. So this is nice. So once we have come to this particular expression, we can now say, why not perhaps integrate everything? So let's start by rewriting the final result we had on the previous page. A dot product by dA is equal to nabla acting on some vector A, all that multiplied by A. So if we then sum all these results and we integrate over this particular surface, so we integrate all these results, the fluxes, and then we integrate the left-hand side and do so, of course, on the right-hand side, we then arrive at the following result, that one will be an integral over an area and the other will be an integral over a volume. So we then have some integral over A, which is the vector field A dot product on the area dA. This is going to be equal to some other integral where we have got nabla acting on some gradient, so the divergence of this particular field A all that multiplied by the element of volume d tau. But we have to state something which is important. This left-hand side, this was actually giving us some result based on the surface of this particular cube that we have. So for us to completely describe the whole cube, this particular surface, we have to consider the closed surface integral, not just one side, but the closed surface integral, right? So we're going to say, let this particular surface that we defined at the beginning to be S. Of course, we called it tau, but let's call it S for now. So S is the surface of this d tau or this tau. Then on the right-hand side, we see that's simply a volume integral. And that is equal to dx, dy, dz, which is commutative, right? And so, because of this, we see now we've got a volume on this side, and we've got also, a surface on one side and a volume on the other side. So, this is simply, quite straightforwardly, an integral over a volume, dx, dy, dz, where some side is a dx, some side is a dy, some side is a dz. And of course, this was just simply a volume, of course, an element of volume, we called it tau. Therefore, we've got this expression simply being then a volume integral over tau. Okay? So this is what we have now arrived to, or arrived at. So we can simply box this equation and say that we have now arrived at an equation that describes all that we need to know about this particular integral. So it's a closed surface integral, and this particular surface integral looks at the area field lines which are leaving some surface or penetrating and leaving this surface. We have some source somewhere producing a measurable field of strength given by Gauss's law. And geometrically, this tells us that some volume is enclosed by a field A, and tells us how to measure, right, or how many field lines actually leave. So in other words, it says how field lines spread through space, because they are leaving some source and penetrating this particular surface, and then we can measure the volume in relation to the surface that we have. So if the source is outside the surface, then the divergence theorem cannot be applied. So the source of the field has to be inside this particular surface we're dealing with. It cannot be outside. So the position of the source relative to the surface is important. Please subscribe, and we're going to continue with our derivations. See you on the next one.